Good morning and welcome to the 30th lecture of the course Water Resource Systems, Modeling Techniques and Analysis. In the last lecture, I introduced the concept of chance constrained linear programming. Recall that when we treat the randomness in the inflows, we can no longer write the constraints in their deterministic form. Because the inflows are random, we have the probability distributions associated with inflows, and these probability distributions we have to explicitly include in the optimization problem. We are talking about the explicit stochastic optimization, and the chance constrained linear programming problem is a optimization problem that belongs to the class of ESO or the explicit stochastic optimization. And therefore, the constraints such as RT greater than or equal to DT, for example, the release being greater than or equal to demand, can no longer be written in that form, because release is also a function of the inflows, and inflows being random, the releases will also be random, and therefore, any constraint that contains release will also have to be written in the form of the probabilistic constraints or the chance constraints. And then we went on to discuss the deterministic equivalents, because once you have the chance constraints, you cannot use the algorithms, the simplex algorithm etcetera straight away, because the chance constraints have to be converted into their deterministic equivalent, and then you use your simplex algorithm or whatever software that you have for solving the linear programming problem on this deterministic equivalent. So, in the last class, we checked how we convert the chance constraint of the form probability that RT greater than or equal to DT greater than or equal to alpha 1. This is a chance constraint. Your original constraint was simply RT greater than or equal to DT. Then we are saying that to write it in the form of a chance constraint, we are saying probability that RT greater than or equal to DT must be at least equal to alpha 1. So, we may specify alpha 1 to be 90%, 95%, 80% and so on. So, we are saying the probability that RT greater than or equal to DT is at least equal to say 90%, say 95% and so on. And then to convert this chance constraint into a deterministic equivalent, we used what is called as a linear decision rule. Remember, linear decision rule we use mainly because we want to apply these chance constraints in the linear programming problems, and therefore, we want to have a linear relationship between the various variables. That is the first reason. The second reason is that there are two random variables. As you can see, RT is related to ST as well as QT. The distribution of QT is known, whereas the distribution of ST is not known. By writing a linear decision rule, what we are achieving in essence is that the complete variability in QT is transferred to RT straight away, and without treating ST as a random variable. So, that is what we achieve. Refer to the previous class on details of this LDR. Using such a LDR and using the distribution of QT, we write the deterministic equivalent of this particular constraint as dt plus bt minus bt minus 1. The bt's are what are called as the decision parameters, and these are deterministic. By using such a form of the LDR, we have also converted ST into a deterministic parameter. Recall in the previous class we said ST is equal to BT minus 1 is what we get as a result of this particular LDR. Now, the deterministic equivalent of this constraint now, this chance constraint was written in this form dt plus bt minus bt minus 1. dt is the demand during the time period t, which is known. Bt and bt minus 1 are decision parameters, these are deterministic, and the right hand side f qt inverse 1 minus alpha 1 is the particular value of the flow associated with a CDF of 1 minus alpha 1. So, that is the interpretation of f qt inverse 1 minus alpha 1. So, you fix 1 minus alpha 1 and then pick up the associated value of Qt on this particular CDF, and that is what gives you the right hand side value. So, the right hand side value will be a known quantity if you have the CDF. dt is a known quantity which has been pre-specified. bt and bt minus 1 become the decision variables, they are the decision parameters. So, this is how we converted the chance constraint into a deterministic equivalent. Like that, we converted all other chance constraints also. For example, the one associated with the maximum release, the one associated with the minimum storage, the one associated with the maximum storage, etc. All these constraints we converted into deterministic equivalent. So, we will now write down the complete deterministic equivalent of the original problem. Now, the original chance constraint problem was this. We were looking for minimize k subject to probability of RT being greater than or equal to dt greater than or equal to alpha 1, probability of RT being less than or equal to RT max greater than or equal to alpha 2, probability of ST being less than or equal to k greater than or equal to alpha 3, and probability of ST being greater than or equal to S min greater than or equal to alpha k alpha 4. Now, of course, when you are using it in a linear programming form, the non-negativity constraints will also come in. So, this we converted into an equivalent deterministic equivalent. We say minimize k subject to this condition now has been converted into this constraint dt plus bt minus 1 less than or equal to f q t inverse 1 minus alpha 1. This constraint is converted into this. Now, the constraints containing ST will become straight away deterministic because ST is equal to BT minus 1. We said that the random variable ST is in fact treated as a deterministic variable BT minus 1, and that is why these constraints which are related with ST, they become deterministic straight away. So, we do not write alpha in terms of alpha 3 and alpha 4, and these are the non-negativity constraints because BT is a decision variable, K is a decision variable, they are non-negative. Now, there are certain small things that you must remember here, not really small, quite important, but subtle issues. One is we said these are alpha 1, alpha 2, etc. These are the probabilities. For example, we are saying that probability of RT being greater than or equal to dt must be greater than or equal to a certain level of probability. We may say it is 0.9, 0.7 and so on. We can change these probabilities with respect to t. So, I may write this as alpha 1 t. For different time periods, I may specify different reliabilities. For example, if you are looking at a monthly operation, you may say that the probability of meeting the demands during the deficit periods must be high, or during the periods in which the demands have to be met, or these are the critical periods. You may want to place the reliability to be high of the order of 0.9, 0.95 and so on. But there may be certain other periods where you can afford to relax a bit, and therefore, you can specify the reliabilities to be smaller. So, like this, the reliability levels here, the probability levels can be different for different time periods. That is the one thing. The second issue is that we said BT is greater than or equal to 0. Look at the LDR. We have used this particular LDR, RT is equal to ST plus QT minus BT. What we are saying here is that the release is a function of the total water available ST plus QT. We are ignoring the evaporation in all these discussions. It can be readily incorporated, but for clarity and simplicity, we will for the time being we will not worry about the evaporation. So, this is the total water available ST plus QT, and you are saying that out of ST plus QT, I will retain BT and then release the remaining amount. That is the idea there. And therefore, BT has to be non-negative here, because there is a total water available ST plus QT, out of which you are retaining certain amount and then releasing the remaining amount. But there are certain other forms of the linear decision rule in which you can make BT to be non-negative also. You can allow BT to take values, not non-negative, to take negative values also, which means you can allow the BT to be unrestricted in sign. We will see one of such linear decision rule in the today's class. So, these are the two things. So, similarly, you may have S mean as a function of t, and then alpha 2 will be a function of t, and so on. So, you can have all of these changing across time periods. Of course, k cannot change with time period. We are talking about the capacity of the reservoir. So, that is one value, not changing with respect to time. Now, this becomes a deterministic equivalent. You can solve this problem using any of the LP solutions. So, you have to specify alpha 1, specify alpha 2, specify dt, which is a data demand, specify RT max, specify S min, and then you will be able to solve this example. Now, these are constraints written for all time periods. If you are talking about a monthly operation, you will have 12 constraints associated with each of these, 12 constraints associated with each of the sets of constraints that I have written here. All right. Now, when we are doing this problem, when we are solving this problem for a 12-month period, the last time period, for example, when we are writing for t is equal to 1, you have a BT minus 1 here. So, when t is equal to 1, you will write this as B1 when I will write that again. What we are saying there is, so when t is equal to 1, it becomes B0, and B0 will set it as B12. So, remember this, that you have t is equal to 1, t is equal to 12, and then this is t is equal to 1. So, the time period previous to t is equal to 1 is t is equal to 12. So, we will write it as B12. That is one thing. So, for steady state solution, we write it as B0 is equal to B12. Then, as I mentioned, you can also set BT to be unrestricted in sign. For example, you may take RT is equal to ST minus BT. This is another form of the LDR, in which we are not accounting for QT. All we are saying is, from the available storage, you retain BT and release only ST minus BT. Now, in this case, BT can be made unrestricted in sign, which means that BT can be allowed to take negative values. What happens if a particular BT turns out to be negative in your optimal solution? It would indicate that RT is equal to ST plus BT with that value of BT, which means that you are releasing more than what is available in the storage. How is it possible? It is possible because you have not accounted for the inflow. So, part of the inflow should take care of this negative value of BT. So, in the form of LDR that we are using, RT is equal to ST minus BT, we can allow BT to be negative. Okay. Now, what we will do is, we will solve a numerical example. These are all concepts that we have covered. We will solve a numerical example and then look at how we obtain the reservoir capacity when we incorporate all the constraints that involve either QT directly or RT and ST, which are functions of QT, as chance constraints. We form them as chance constraints and formulate the deterministic equivalent of that, and then solve the linear programming problem. That is what we will do now. So, the first example that I will consider now is that we will take the LDR as RT is equal to ST plus 1 minus zeta QT minus BT, with zeta varying between 0 and 1. So, recall in the last lecture I explained the general nature of the LDR, where we are accounting for a proportion of QT in the linear decision rule. So, QT is the inflow. We are saying that in making the decision RT, we will look at some proportion of the QT, because zeta varies between 0 and 1, we may say that zeta is equal to 0.5, let us say, which means that we are saying 50% of the QT is taken into account while making the decision RT. So, that is the idea. So, we use this LDR now and we will obtain the deterministic equivalent of this constraint, probability of ST being less than or equal to k, greater than or equal to 0.8. As I have been mentioning, QT being the random variable, that is the inflow during time period T being the random variable, we need the distributions of QT, that is the CDF or the PDF. From PDF you can always obtain the CDF in several cases. So, we need the distribution. So, in this particular case we will assume QT to follow an exponential distribution with the PDF. I will write it here more clearly, f of q is equal to beta e to the power minus beta q. So, this is the exponential distribution. So, we will assume that in all the time periods QT follows an exponential distribution, but the parameters are different. This has a single parameter beta. So, in time period T is equal to 1, beta is equal to 2, T is equal to 2, beta is equal to 5 and so on. So, 2, 5 and 7. So, the beta parameters are given for these 3 time periods and therefore, the f of q is completely defined for all the 3 time periods. Now, this is the chance constraint we are writing. Now, k is a known reservoir capacity in this particular case. So, k we will keep it as constant or deterministic, and this right hand side, which is the alpha level or the reliability level, is fixed, which is given as 0.8, and we will neglect the evaporation loss. So, for this problem, for each of these time periods, we must be able to write the deterministic equivalent. The LDR here is specified as ST plus 1 minus zeta QT minus BT. We will use the continuity equation. This is the continuity equation by when we neglect the evaporation loss. So, ST plus 1 is equal to ST plus QT minus RT. This is the continuity equation. So, I will use the LDR now. I will rewrite this as ST plus QT minus, for RT I will substitute the LDR, and then I get ST plus 1 as zeta QT plus BT. So, ST plus 1 is this, and therefore, I will write ST as zeta QT minus 1 plus BT minus 1, because I am writing it for T. Now, zeta is a value between 0 and 1. This will be specified when we are doing any application. So, right now we will retain it as zeta, but remember that zeta varies between 0 and 1. So, the LDR reduces to this form now. Now, we will look at the deterministic, we will formulate the deterministic equivalent of this. We are saying probability of ST being less than or equal to k is greater than or equal to 0.8, and ST is zeta QT minus 1 plus BT minus 1. So, I will write this as zeta QT minus 1 plus BT minus 1, that is the probability of zeta QT minus 1 plus BT minus 1 less than or equal to k must be greater than or equal to 0.8. This is what I write. Remember always that you bring the random variable to the left hand side of the inequality, because you know the probability distribution of the random variable. Take out all the deterministic variables and the parameters to the right hand side of the inequality. That is what we will do now. So, zeta QT minus 1, QT minus 1 is the random variable, less than or equal to k minus BT minus 1, greater than or equal to 0.8. Remember, we are writing this for time period T, because we are saying ST must be less than or equal to k. But the moment we use this LDR, we have brought in BT minus 1 here, that is time period T minus 1. So, when we are writing the constraint for time period T, we are looking at the distribution of the inflow in the previous time period T minus 1. So, these issues you must keep in mind. So, I will write this as probability of zeta qt minus 1 less than or equal to k minus bt minus 1 greater than or equal to 0.8, and I will write this as probability of qt minus 1 less than or equal to k minus bt minus 1 zeta greater than or equal to 0.8. Now, what is this term now? This term is, it reflects, remember that f of x is equal to probability of x being less than or equal to x. So, this indicates the CDF associated with this value. Now, this value here is k minus bt minus 1 over zeta. K is deterministic, bt minus 1 is deterministic, zeta is a specified value, and therefore, this is a deterministic value. So, we will write this as f qt minus 1, indicating that we are talking about the distribution of qt minus 1 of k minus bt minus 1 zeta greater than or equal to 0.8. Now, this we write again using our earlier notation, k minus bt minus 1 over zeta is greater than or equal to f qt minus 1 inverse 0.8. I repeat again, because students tend to make this mistake often. What we mean by this is that associated with the f value of 0.8, you pick up the qt minus 1 value. So, these are the qt minus 1 value, and this is f qt minus 1 on the y axis. So, this indicates that it is that particular value of qt minus 1 which leads to a f value of 0.8, that is the idea there. So, this can be got once the distribution is given, and this is a known value or a decision variable, deterministic. This is a deterministic decision variable, and this is specified. Therefore, this becomes a deterministic equivalent. Now, it is given that f of q is a exponential distribution. So, we have beta e to the power minus beta q for q greater than 0 for all the time periods, but the beta is different for different time periods. Now, recall that the exponential distribution has a CDF. Starting with this, you can also integrate. The CDF is simply minus infinity to x f of x dx. This is f of x. So, in the previous lecture or lecture previous to that, we have discussed the exponential distribution. So, the f of q can be written as 1 minus e to the power minus beta q, q greater than 0. Now, what is it that we are doing? We want to write this set of equations now, set of inequalities or the set of constraints for all the time periods t. So, we need this value now, f qt inverse qt minus 1 inverse 0.8. This is the value that we need. To get this value, we go to the distribution of qt. Now, we have said that qt follows an exponential distribution in all the 3 time periods, but with different parameters. So, beta 1 is different from beta 2 is different from beta 3. So, we will write for t is equal to 1. Now, when t is equal to 1, the previous time period will be t is equal to 3, which is the last time period in the year. So, t is equal to 1 implies that t minus 1 is equal to 3. This is the previous time period when we are talking about the first time period. So, look at this expression now, k minus bt minus 1 zeta over zeta greater than or equal to f qt minus 1 inverse 0.8. So, when I am writing for t is equal to 1, I will pick up these values corresponding to t minus 1 is equal to 3. So, I will write this as k minus b 3 by zeta greater than or equal to f q 3 inverse 0.8 by setting b naught is equal to b 3, like I explained just now. Now, which means for the distribution of q 3, you go to 0.8. So, you look at the distribution of q 3 now. So, you will look at f of q 3 and then go to 0.8 and then pick up that particular value associated with 0.8. That is what you have to do. So, this is 0.8, we are talking about this particular value. which means from the f of q expression here, you have the expression for f of q. You need f q inverse 0.8, which means that you are setting f of q is equal to 0.8. So, I will put this as 1 minus e to the power minus beta q 3 as 0.8, and beta for time period 3 is 7, that is the data that is given. So, beta is 7 for time period 3. And why I am using time period 3? Because we are writing it for t is equal to 1, the previous time period t minus 1 is 3, and that is why I have to pick up for time period 3. So, 1 minus e to the power minus 7 q 3 is equal to 0.8, and therefore, q 3 turns out to be 0.23, which means this value here turns out to be 0.23. Therefore, I write this as k minus b 3 by zeta is greater than or equal to 0.23. Similarly, for t is equal to 2, when I am writing, it will be k minus b 1 divided by zeta greater than or equal to f q 1, that is the distribution associated with the random variable q 1 inverse 0.8. Then I apply the same thing, and beta 1 is beta 2 is given as 5 and beta 1 is given as 2. So, I will write this as for time period 1, I will write it as 1 minus e to the power minus 3 q 1 is equal to 0.8, and that you can verify that q 1 turns out to be 0.536. Similarly, for t is equal to 3, I do the same thing. I am referring to time period 2 then, and then I use the distribution for time period 2, that is q 2, and then get q 2 is equal to 0.322. And therefore, the deterministic equivalence for that particular constraint, namely that probability of S t being less than or equal to k greater than or equal to 0.8 for all t, that is t is equal to 1, t is equal to 2, t is equal to 3. This is the constraint that we are considering. The deterministic equivalents come to be k minus b 3 over zeta is greater than or equal to 0.23, and so on. This is what we obtained in the exercise now. So, for one set of constraints like this, we write the deterministic equivalent during all the time periods. In this particular example, we had 3 time periods. So, associated with each of these time periods, we write the deterministic equivalents. Remember, this is a known parameter here, this is known, that is we would have specified zeta to be 0.5, 0.6 and so on in the LDR, and k is known or to be determined, but it is a deterministic parameter. B 1, B 2, B 3 have to be determined, they are deterministic parameters, and therefore, this constraint set is completely deterministic. You can use them in the linear programming problem. So, like this, each set of constraints you convert them into deterministic equivalents and then form the complete LP package, which will be a deterministic problem. You can use any of the softwares to solve the problem. We will now revisit our original problem, which is we are looking at the minimum reservoir capacity associated with the chance constraints, subject to the chance constraints, namely probability of R t being less than greater than or equal to d t greater than or equal to alpha 1 and so on. So, we will revisit that and solve a numerical example, so that you know from beginning to end how to solve the problem. As I have been mentioning, to solve the numerical example or to solve a chance constraint LP, you need the distributions of the QT. QT is the only random variable we are taking, but because QT is a random variable, RT becomes a random variable, ST becomes a random variable, and depending on the type of LDR that you use, linear decision rule that you use, you will get different forms of the deterministic equivalent. So, the first step is to see the to obtain the probability distributions of QT. If you are talking about a 12 time periods, monthly time periods, you should have the distribution of Q1, Q2, Q3 etc. up to Q12. All these distributions may be different from one another, or they may follow the same distribution, but with different parameters, which essentially means that the distributions are different. Then that is the one first thing. Second thing is you are saying that probability of RT being greater than or equal to DT. So, the DT set must be given, demand set must be given. Then you are saying probability of ST being less than or equal to K. K is the decision variable, which is the capacity. This can be converted into deterministic equivalent as we did just now. Like this, whatever the constants that go into the problem must be determined a priori. So, we will solve an example now, and then after converting the problem into a deterministic equivalent, you should be able to use any of the LP algorithms, LP packages to solve the problem. So, we will do a complete exercise now, starting with the original statement of the deterministic problem and then converting this into the chance, I am sorry, I will repeat that, starting with a original statement of the chance constrained LP problem CCLP, and then convert that into a deterministic equivalent, then use numerical values and then solve the problem completely and interpret what it means. So, this is our original problem, that is you are looking at the minimum capacity K subject to the ST, which is the storage at the time period, at the beginning of the time period T, must vary between S min and K. So, the probability of storage being in this range is greater than or equal to 0.9. This is a chance constraint. Why we write it as chance constraint? Because ST is a function of QT. QT is a random variable, QT is the inflow to the reservoir during the time period T, that is a random variable, and therefore, ST becomes a random variable. Therefore, we write this in the form, in this particular form, in the chance constraint form. Then we have probability of RT being less than or equal to RT max. This is the maximum release during time period T, must be greater than or equal to 0.95. Then probability of RT being greater than or equal to DT, this is the demand during the time period T, must be greater than or equal to 0.75, which means we are saying that at least 75% of the time my releases must be greater than or equal to the demands. Now, depending on the type of linear decision rules that we use, as indeed we have shown in the earlier type of linear decision rule, ST may turn out to be a deterministic parameter, but we will now see that it is in fact not so in general. So, we will use a particular linear decision rule of the form RT is equal to ST minus BT. The LDR that we used earlier was RT is equal to ST plus QT minus BT, but now what we will do is we will simply say RT is equal to ST minus BT. So, we using this LDR, we will convert this chance constrained LP. Now, the way we have formulated this is called as the chance constrained LP, CCLP. This will convert it into a deterministic equivalent. As I said, for us to be able to convert the chance constrained LP into a deterministic equivalent, you need first the distributions of the flows, probability distributions of the flows. So, we have this here up to this point, the probability distribution values. That means, what does this indicate? That it indicates, let us say for a particular time period, you have a CDF and the values that we are giving here are associated with, let us say this one 0.25. So, I take 0.25 here and I come down, this value will be 33 for time period T is equal to 1. This is 0.25. So, this is what it means. F inverse 0.25 is 33. F inverse 0.75 will be 60. Let us say 0.75 is here somewhere, and then this goes on like this. So, that is 60. and so on. So, this indicates for any time period t. So, I am writing it for time period t is equal to 1. These values are given now, which means the CDF values associated with probability of 0.75, 0.25, 0.10, etc. are given, 0.9, 0.95 and so on are given. Then these are the constant values R max, R min and S min. They appear here, S min appears here, R max appears here, and dt is also dt is we have taken to be known, but I have not specified the dt values here, but S min that appears here is given, and you also have R min. R min is the dt in fact. So, R min is a minimum release, which is not this one, this is a minimum release, this is I will write it as R min t, minimum release or demand. All right. So, we need these values now, namely dt we need, which is the R min given, RT max we need for each of the time periods, S min we need. So, these are the values that are given here. So, R max is given, R min is given, which is dt, and S min is given. So, we have the probability distributions of the flows, we have all the constants that are necessary. Now, we will go to convert them into deterministic equivalent. Always we start with the linear decision rule, use the reservoir continuity equation, and then see how ST can be expressed in terms of QT, QT minus 1, BT, BT minus 1 and so on. So, we use the linear decision rule, which is in terms of RT, which relates RT with respect to ST and QT minus 1 with BT and so on. So, we will start this RT is equal to ST minus BT, and this is a reservoir continuity. So, I will write this as ST plus QT minus RT, RT is ST minus BT. So, I will write it as minus ST plus BT. So, this turns out to be ST plus 1 is equal to QT plus BT, and therefore, I write ST is equal to QT minus 1 plus BT minus 1. And then we go on to write deterministic equivalents associated with each of the constraints. The first constraint here is written as probability of ST being in the range S min and K is greater than or equal to 0.9. Now, this will split into two constraints. One is we take the left hand side. So, probability of ST being greater than or equal to S min is greater than or equal to 0.9. The second one is probability of ST being less than or equal to K is greater than or equal to 0.9, which means what we are saying is that probability that ST is greater than or equal to S min as well as probability of ST being less than or equal to K must be greater than or equal to 0.9. So, this we write as two different constraints. Now, we will start with the first constraint now. We write probability of S min less than or equal to ST greater than or equal to 0.9. Remember, S min is known, this is known, and ST is a decision variable in terms of QT minus QT. So, from here we have got ST as QT minus 1 plus BT minus 1. So, I write in terms in the place of ST, I write it in terms of QT minus 1. Remember, all the constraints which contain the variables ST, RT, etc., which are functions of the random variable QT must be written in terms of the random variable QT, because we know the distributions of the inflow QT. So, all these constraints have to be written expressed in terms of the inflows, be it the QT, QT minus 1 and so on. So, you may, depending on the type of LDR that you have used, you may get different terms associated with the inflows. So, here I am writing ST as QT minus 1 plus BT minus 1. So, we bring the random variable to the left hand side of the inequality. So, I write this as QT minus 1 plus BT minus 1 greater than or equal to S min greater than or equal to 0.9. Then I will write this as probability of QT minus 1 greater than or equal to S min minus BT minus 1. I have taken the BT minus 1 to the right hand side greater than or equal to 0.9. then I write this as probability of Qt being less than or equal to S min minus Bt minus 1 less than or equal to 1 minus 0.9. I am changing the inequality sign inside, therefore, this becomes 1 minus 0.9. Refer to the last class where I discussed this. So, because you change the inequality sign inside and you are talking about the probabilities, this will change the sign as well as this will be 1 minus of this value. So, I will write this as probability of Qt minus 1 less than or equal to S min is 2 minus Bt minus 1 less than or equal to 0.1. Now, what is this now? This is probability of x being less than or equal to x, which means I will write this as probability of f of Qt minus 1 of 2 minus Bt minus 1. This subscript Qt minus 1 indicates that we are talking about the distribution of Qt minus 1. 2 minus Bt minus 1 less than or equal to 0.1, or we write this in our usual notation as 2 minus Bt minus 1 less than or equal to f Qt minus 1 0.1. Now, this is where we use the data on the distribution. Now, this particular equivalent, deterministic equivalent, I have to write for t is equal to 1, 2 and 3. So, when I write for t is equal to 1, your Qt minus 1 will be 3, because there are 3 time periods. So, Qt minus 1 will refer to Q3 or t minus 1 refers to 3, and we go to time period 3 and pick up that particular value associated with f Qt inverse 0.1. So, when I am writing for t is equal to 1, I am writing 2 minus B3 less than or equal to f Q3 inverse 0.1. Now, f Q3 inverse 0.1 is given here in the table. You just go there, you are referring to time period 3 and 0.1. So, this is 6. So, that is what I pick up and write this as 2 minus B3 is less than or equal to 6. So, this 6 is obtained by distribution of Q3, obtained from distribution of Q3. So, this becomes the deterministic equivalent 2 minus B3 less than or equal to 6. Now, I go to time period t is equal to 2. I am writing this expression for t is equal to 2. Therefore, 2 minus B2 minus 1, which is B1 less than or equal to Qt minus 1, which will be Q1 inverse 0.1, which means I go to the distribution of Q1 and then pick up Fq inverse of 0.1. This is given Fq inverse of 0.1, which is 12. So, I write this as 2 minus B1 less than or equal to 12. Similarly, when I write for t is equal to 3, I pick up the value from distribution of t is equal to 2, which is 3. So, I will write this as t is equal to 3. So, like this, the first constraint, which is probability of S min less than or equal to S t greater than or equal to 0.9, is now converted into this set of constraints for t is equal to 1, t is equal to 2, t is equal to 3. Similarly, we write this deterministic equivalent of S t less than or equal to k greater than or equal to 0.9. I leave it as an exercise, but this is what you get here. So, use the same logic and then use the data, you will get k minus B3 greater than or equal to 72, k minus B1 greater than or equal to 90, k minus B2 greater than to 60 for t is equal to 1, 2 and 3. Similarly, the deterministic equivalent of probability of RT being less than or equal to RT max greater than or equal to 0.95, this leads to 90 plus B1 minus B3 greater than or equal to 85, 84 plus B2 minus B1 greater than or equal to 93, 84 plus B3 minus B2 greater than or equal to 80 for t is equal to 3. Just verify these. So, we have written also for probability of RT being greater than or equal to DT greater than or equal to 0.75. This leads to 24 plus B1 minus B3 less than or equal to 21, 20 plus B2 minus B1 less than or equal to 33 and so on. We use the same procedure for each of the constraints. The probability constraints are expressed in their original form in terms of ST or RT. Using the LDR, you express these probability constraints in terms of the random variable qt, qt minus 1, qt minus 2, etc. And then using the associated distributions, probability distributions, you can express them as deterministic equivalents. So, this is a general procedure, and that is how we obtained all these equivalent deterministic equivalents, and then you also put the data that is given to you and then write them in terms of the numerical values. So, then if I write the complete deterministic equivalent, it looks like this. This is the set corresponding to the first set of constraints, this is second set of constraint, third set of constraints, fourth set of constraints. And then you look at this, we are looking at the minimized value of k subject to all these constraints. So, what are the decision variables in this problem? The decision variables are b1, b2 and b3 and k. So, you will obtain, when you solve this problem, you will obtain the solution as k is equal to 90, b1 is equal to 0, b2 is equal to 9, b3 is equal to 5. Now, this is the solution that you obtain when you solve this problem. Remember, the particular LDR that we used for this example is RT is equal to ST minus BT, which means now the BT that you have used here can be left unrestricted in sign. That means, we can allow the BT to also take negative values. So, I suggest you do the problem both ways. First, you take BT greater than or equal to 0, that means, do not allow the BT to take negative values and then obtain the solution. You also allow the BT to take negative values and then obtain the solution and compare the two solutions. Remember, when we write RT, the physical significance of this is that when you write RT is equal to ST minus BT, you are being conservative, you are not allowing for the information content in Qt, that is what is the likely value of Qt that is coming during the time period t is not accounted for when you are writing this. And therefore, when you allow BT to take negative values, you are saying that RT can be greater than ST, because then it will become RT is equal to ST plus BT. So, RT can be greater than BT in certain time periods, in which case you are allowing for part of the inflow to be also accounted for. So, that is the interpretation of this. So, I encourage you to solve the problem on both with both conditions, one BT being non-negative and another BT being unrestricted in sign. And how to solve these problems I have discussed earlier, you can just solve the problem using both. Now, the optimal solution that you get here is k is equal to 90, b1 is equal to 0, etc. Look at the optimal solution. It says that the minimum storage required is 90 units, and the associated values of B1, B2, B3 are also given, which means that you need to operate this particular reservoir also in that particular form, that is RT is equal to ST minus BT, where BT is specified now. Look at the storage, ST minus BT is the release during that time period. So, you have the storage as well as the release policy both built together in this optimal solution. Now, what does this mean? This also means that it is a steady state solution, in the sense that from year to year you will adopt this particular policy of operation. In that case, it becomes optimal, in the sense that you are able to meet the demands at least 75% of the time, you are able to meet the storage restrictions at least 90% of the time, 95% of the time, etc., consistent with the probabilistic constraints that we stated in the problem. So, that is the interpretation of the chance constraint optimization. Remember, just to summarize quickly the chance constraint optimization problem. In the chance constraint optimization problem, we specified the original constraints of the form RT greater than or equal to DT as probabilistic constraints, probability of RT being greater than or equal to DT greater than or equal to alpha 1 and so on. And then we obtained the solutions using the deterministic equivalents. So, essentially what we did there is, that a constraint of the form probability of R t greater than or equal to d t greater than or equal to alpha 1, let us say. Now, this is the chance constraint. Your original deterministic constraint was R t greater than or equal to d t. That means, you wanted to meet the demands during time period t with 100% reliability. This was the interpretation, this was the deterministic constraint, original deterministic constraint. And this is a chance constraint. Or reliability constraint. Or probability constraint. Now, what we did is, because R t is a random variable by virtue of it being a function of the inflows which are random variables, we cannot write this in deterministic form, and therefore, we wrote this as a chance constraint of this form R t greater than or equal to d t greater than or equal to alpha 1, and then we specified alpha 1. And then we evolved methodologies of converting this chance constraint into deterministic equivalent. Now, there are some interesting issues here. One is specifically for this particular type of constraint, where we are saying that the release should be greater than or equal to the demand, and therefore, the level alpha 1 that we specify here indicates the reliability of meeting the demands. So, this is the reliability. What I mean by that is that by writing this, specifying this particular constraint, we are saying that the reliability of meeting the demand d t in time period t through the release R t is at least equal to a given level alpha 1. We may say, as we did in this example, we may say this is 0.75. That means, the reliability is at least 75%. It can be more, but the minimum reliability we are specifying there. Reliability of meeting the demand is at least 75%. Now, we were obtaining a given reservoir storage by specifying the reliabilities. You look at the problem in slightly different way. You have a given reservoir storage, that means, K is specified. You are solving this for an existing reservoir operation, reservoir problem. And then we are saying that probability of R t being greater than or equal to d t is greater than or equal to alpha 1. Now, there the problem is slightly different. You may want to optimize the operation, optimize the reservoir operation, such that 75%, 85% etcetera are the minimum reliabilities with which you are able to meet the demands. Now, I will pose the problem in a slightly different way, that you have the given reservoir and you want to meet the demands with the highest reliability. That means, we are not pre-specifying the reliability, we will say that we want to maximize the reliability with which the demands can be met. So, that is the problem that is addressed by what is called as reliability programming. Those who are interested can refer to some earlier papers by Simonovic and Marino, who introduced this concept. I think in late early 1980s or something, somewhere around 1980s, you refer to these papers. There is a series of 3 WRR papers by Simonovic and Marino that introduces the concept of reliability programming. You must understand what is the concept here. When I write a constraint of the form probability of R t being greater than or equal to d t greater than or equal to alpha 1 or alpha, let us say. Now, this alpha, instead of pre-specifying the value of alpha, I will make alpha also as a decision variable. and I will look for maximization of alpha itself in some sense. So, I will say that I want to look at the maximum reliability that we can get from this system, maximum reliability of meeting the demands. Now, this turns out to be a non-linear optimization problem, because RT is a function of QT, and when we are looking at alpha being a decision variable here, because of the deterministic equivalence of this, you will get these constraints in terms of f inverse of alpha, and those f inverse of alphas will be all non-linear values, because you are talking about a CDF there, and therefore, the reliability programming in general is a non-linear problem. So, this just remember. So, we will close the discussion on the chance constrained linear programming now. What I would like to specify before I close, just as a matter of closure of the topic, is that the chance constrained LP is in fact a good handy tool as an explicit stochastic optimization technique. However, if you want to use linear programming, then you have to necessarily use linear decision rules, and also because there are several random variables associated, several random variables involved in the constraints. Writing down the deterministic equivalents without the LDR will be extremely difficult and involved, because you are talking about distributions of 2 random variables as a function of 1 random variable. Qt is the only random variable for which you can estimate the distributions, but this distribution information has to be transferred to 2 random variables St and Rt. So, if you do not use the linear decision rule, then the problem becomes extremely complex. But the linear decision rule itself is a sort of not a very straightforward way of handling the random variables, because we are saying that one of the random variables can be simply treated as deterministic equivalent, deterministic variable, and so on. The chance constrained linear programming can be extended to linear reliability programming by also making the reliabilities themselves as decision variables. So, for a given reservoir system, we may start talking about what is the maximum reliability of meeting the demands, and these type of problems are especially relevant, especially important in the case of hydropower generation, where you have the infrastructure in place, the hydrology is random, and therefore, you would like to maximize the reliability of hydropower production. So, you will let the alpha itself as a decision variable, and then start looking for what is the maximum reliability that you can obtain from such a particular reservoir system by operating it in an optimal manner. So, the operating policy becomes the decisions to be made, and the reliability becomes a decision variable. So, you will be essentially looking at the maximum reliability, and this type of problem is typically addressed through the reliability optimization or reliability programming problems, and these always turn out to be non-linear problems. You cannot use the linear programming for solving such problems, and some literature is available on reliability programming problems. The students who are interested in pursuing this along these lines must refer to the earlier papers by Simonovic and Marino somewhere around 1980s. They are the classical problems, classical papers on reliability programming. So, in the next class, we will introduce the important topic of stochastic dynamic programming for reservoir operation. Thank you for your attention.